Hi all, welcome to the practice assignment sessions of the NPTEL course Introduction to Wireless and Cellular Communication. Here I'll be discussing the practice assignments for various weeks depending upon the subject content dealt with in the NPTEL course. Okay, let's get started. In a digital communication system, the following impairment is always present. The options are inter-symbol interference, co-channel interference, adjacent channel interference, thermal noise. So, which of the following impairments is always present? So, the answer is inter-symbol interference. Inter-symbol interference is credited by multipath reception within time-dispersive channels. Generally, digital data is represented by electric pulse and the communication channel is always band-limited. Such a channel disperses or spreads a pulse carrying digitized samples passing through it. When the channel bandwidth is greater than the bandwidth of the pulse, the spreading is very less. But when the channel bandwidth is lesser than or closer to the signal bandwidth, that is like if we transmit digital data which demands more bandwidth which exceeds the channel bandwidth, spreading will occur and it will cause the pulses to overlap. This overlapping is referred to as inter-symbol interference. Okay, so let us move on to the next question. If received signal is affected by inter-symbol interference, the method of compensation is dash. So how do you compensate inter-symbol interference at the receiver? So time synchronization, equalization, increasing sampling rate, none of the above. So the answer is equalization. An equalizer within a receiver compensates for the average range of expected channel amplitude and delay characteristics. So basically the equalizer at a mobile receiver is like a filter whose impulse response is inverse of the channel's impulse response. So this helps us to combat inter-symbol interference. In a digital communication system, the role of forward error correction or FEC is to address dash. So the options are time synchronization, frequency offset, channel-induced errors, none of the above. The answer is channel-induced errors. Basically, the role of FEC is to address channel-induced errors. The transmission of signal through the channel may introduce errors in the data transmitted. So, forward error correction or FEC helps us to detect and correct a limited number of errors in the transmitted data without the need for retransmission. In this method, the sender sends a redundant error-correcting code along with the data frame. The receiver performs necessary checks based on the additional redundant bits. If it finds that the data is free from errors, then it executes error-correcting code that generates the actual frame. It then removes the redundant bits before passing the messenger to the upper layers. So FEC helps us to correct channel-induced errors without retransmission. So the next question. A link budget is a way of computing the following: the transmit power needed for the system, the maximum distance between the transmitter and the receiver, the SNR that can be achieved at different distances from the transmitter, or all of the above. So the answer is all of the above. In the design of wireless communication links between two sides, issue of range, throughput, and received signal quality are of great importance. The link budget analysis shows all the gains and losses from the transmitter through the medium to the receiver in a telecommunication system. Hence, it is a way of computing all of the above. So the next question. Suppose a digital communication system uses a baud rate of 1 kilobaud and achieves a rate of 3 kilobits per second. What are the possible modulation schemes that can achieve this? The options are binary phase shift keying, quaternary phase shift keying, iterary PSK, and a 3-level modulation. Basically, the baud rate is 1 kilobaud and it should achieve a rate of 3 kilobits per second. So the answer is iterary PSK. So let's see how. So the baud rate or symbol rate is equal to number of bits transmitted per second. For memory PSK, baud rate is equal to bit rate by log m to the base 2. Or in other words, we could say that bit rate is equal to baud rate into log m to the base 2. So here we know the bit rate is 3 kilobits per second and the baud rate is 1 kilobaud, which means log m to the base 2 is equal to 3. So which means that m is equal to 8. So the answer is iterary PSK. The next question. Consider a speech signal with a bandwidth of 8 kHz. The Nyquist sampling rate is dash. So the options are 8 kHz, 16 kHz, 4 kHz, none of the above. So the answer is 16 kHz. Basically, Nyquist rate is twice the maximum frequency of the signal. So the maximum frequency is actually, so the bandwidth is 8 kHz, hence the maximum frequency is 8 kHz. So it's 2 into 8 kHz, which is 16 kHz. The next question. Consider an RF signal with a carrier frequency as 900 MHz. If a quarter wavelength antenna is to be used for its reception, the dimension of the antenna is approximately dash. So basically, your carrier frequency is 900 MHz and you have a quarter wavelength antenna. So they're asking you to find the dimension. The options are 8.3 centimeters, 33.3 centimeters, 8.3 divided by 2 pi centimeters, none of the above. So the answer is 8.3 centimeters. So first let us find the wavelength. So wavelength is velocity of light divided by carrier frequency. So C is actually 3 into 10 power 8 meters per second divided by FC is 900 megahertz. So I get 3 into 10 power 8 divided by 900 megahertz as 1 by 3 meters. Now the dimension is basically lambda by 4. So that is equal to 1 by 12, which is approximately 8.33 centimeters. Thank you.